Assalamualaikum warahmatullahi wabarakatuh. So for this video, I will cover on the chemistry and separations. Okay, under this subchapter 3.3, I will divide it into two parts. Okay, the first part will be the chemistry and separations. Okay, firstly, I would like to explain about the separation process. Okay. Why we need this separation process? Because we need to do a pre-treatment, product recovery, and also waste processing. So most separation process are based on a moving component from one phase to the another, and then segregating the two phases. So this separation process is driven by activity gradient as phases to reach the equilibriums. Okay, the separation process also affected by rates of mass transfer and also heat transfer. Okay, for the separation specifications, okay, basically for the separations, normally we have a feed containing a mixture of A and B. Okay, it can be more than A and B. Okay, for this case, the mixture is A and B. Okay, this mixture is fed into the column and then it will be separated according their boiling point. Okay, the light key will move upward. Okay, we call product and it is in the gas phase. Okay, meanwhile, the heavy key it is in the liquid phase, will go downward and become a recovery. So recovery is how much of the desired component made to the stream it was supposed to be in. Okay, so to calculate the recovery of product A here, okay, we need to times product flow rate with the mole fractions of A over with the feed flow rate with the mole fraction of the feed of A. Okay, so okay, this flow rate of feed is same as the mass flow rate of P plus with the mass flow rate of R. Okay, so we can expand it by time the product flow rate with the mole fraction of vapor and also plus with the recovery with the mole fraction of liquid. So impact of separation specifications. Okay, in terms of cost, the tighter specification lead to the higher cost. If we need the more purity or higher recovery product, so the cost will be increased. So the final product must meet purity specifications. This is set by the standard of a STM, USP, and there is a few other standard that highlight this purity specifications. Recycle sometimes have purity specifications. Why? Because we want to protect catalysts from contaminant or poisons. Okay, so we have vapor-vapor separations. For the vapor-vapor separations, normally we use a membranes, absorption, and also absorptions. So for the membrane, normally it will be used for the H2 and CH4 system, CO2 removal, and also aspirations. For the absorption, normally we will use for the liquid solvent. We will use a liquid solvent in a absorber stripper, and the application is for acid gases, drying, water wash. Okay. Okay, the other equipment for the vapor separation is absorptions. So absorption we have two types, which is the type of equipment we have two, which is temperature swing absorption and also pressure swing absorption. So the application for this absorption is air separations, H2CH4 separations, and most separations involving low concentrations feed. Okay. Okay, what is absorption? What is absorptions? Okay. For the absorptions is the assimilation of molecular species throughout the bulk of the solid or liquid. Okay, normally when there is a gas that moving to the solid or liquid, then the gas is absorbed to the solid or liquid. That one we call as absorption. Meanwhile, for the absorption is the accumulation of the molecular species at the surface rather than in the bulk of the solid or liquid. That means in the absorption equipment, there is a solid surface, and when the gas pass through the solid surface, it will absorb at the surface of the solid. Okay, so the absorption is a bulk phenomenon, while absorption is a surface phenomenon. The heat exchange occur inside the absorption is endothermic, meanwhile for the absorption is exothermic. So endothermic absorb heat, meanwhile exothermic is release heat. Okay, for the absorption, the temperature is not affected. The absorption process is not affected by the temperature. For the absorption, it is favored by low temperature. So for the rate of reaction for the absorption, it's occur at uniform rate. In the absorption, the rate of reaction steadily increase and reach to equilibrium. So we can see the pattern of the profile of the component or concentration. It will increase until certain point, it will reach the equilibrium point. Okay, for the absorption, the concentration is same throughout the material. So for the absorption, we focus on the concentration on the surface of adsorbent. So the concentration on the surface of the adsorbent is different from that in the bulk. Okay. Okay, so this is the illustration for the absorption and also adsorption. So for the absorption, okay, this is a gas bulk and also liquid bulk. Okay, the gas that flow will absorb to the liquid or gases. Okay, for the liquid bulk here, it will absorb to the solid surface of adsorbent. Okay, now moving on adsorptions. Okay, like what I'm saying before, adsorptions is the mechanism is one component from vapor phase preferentially adsorbed onto the surface of a solid adsorbent. So we have two types of adsorption, which is reversible and also irreversible. So for reversible, the mechanism is physiosorption, while for the irreversible is chemisorption. So for the reversible, its adsorbed component, the absorbed component can be released by decreasing pressure or increasing temperature. Okay, the sorbent can be regenerated and used in multiple cycles. Hence, temperature swing adsorption and also pressure swing adsorptions. So basically, the equipment that being used inside the reversible is TSA and also PSA. Okay, later on I will explain in detail how the TSA and PSA work. Okay, for the irreversible, during the process, the adsorbed component usually react irreversibly with solid. So low concentration can be achieved, but solid is difficult to regenerate. Okay, unlike reversible, the solid solvent can be regenerated. Normally, this irreversible is used for contaminant removal gut bags. Okay, so this is the concentration profile during absorption. Okay, so we can see here the concentration of B on sorbent versus to the distance down to sorbent bed. So basically we can see that the concentration of B will decrease when the bed length increases. That means for example, bed length here, it will increase until this point. Okay, the concentration, we can see here, this is the concentration exists. So this is 0, let's say this one, and this is 1. So at first it start at the higher point, higher concentration, and it will decreases along the bed length. Okay, so for the irreversible absorptions, if the system use 2 guard beds, that means there is 2 bed, 1 bed here and 2 bed here. If this 2 bed is used in a parallel, so when bed 1 new to the breakthrough, that means the bed 1 start to achieve its equilibrium point, the process flow can be switched to bed 2. Some adsorbent will be wasted as bed cannot be run close to breakthrough for fear of contaminant slippage. So normally the beds will be run approximate only to the breakthrough. That means it will achieve to the equilibrium approximately. Okay, now we move to the other type of irreversible adsorption, which is lead-lag guard bed system. Okay, we can see here the figure. The connections of pipe is slightly different as compared to the previous one. So this is the alternative arrangement. So this arrangement is in series. When the upstream bed reaches breakthrough, downstream bed is still okay. So upstream bed can be taken offline, reloaded and brought back into the downstream services. So it can be used in series. So this configuration make more efficient use of adsorbent as compared to the previous one just now. Okay, this is the real figure in industry of the guard bed for mercury capture. So mercury occur in a natural gas and also light oils. So this mercury must be removed to protect the equipment and also catalyst. Okay, this is the reversible absorption. This is the figure, the profile for the reversible absorption. Like irreversible just now, we consider the concentrations of the materials of the gases versus with the bed length. But for the reversible adsorptions, we consider the partial pressure with the mass adsorbed. So reversible adsorption exploit changes in loading with pressure or temperature. So in here we can say that reversible adsorption is depending on the pressure or temperature. Okay, by referring to this graph, we can see that the absorption occurred at P1 and also T1. So it gave a loading of M1. For the P2 and T2, it will give the loading of M2. So for the pressure swing, its working principle, it will decrease the pressure from P1 to P2, and the loading of the adsorbent decrease from the loading of the sorbent will be decreased from M1 to M2. So in order to calculate the total amount of loading, the delta loading, we need to minus M1 with the M2 so that we can know the amount of loading in that system. Okay, this is the working principle for the pressure swing adsorption. So for the PSA, the cycle between high and low pressure to load and regenerate the adsorbent. So we play around with the pressure. It is a cycle between high and low pressure to load and regenerate the adsorbent. Okay, now we move to the TSA. So for the TSA seams, we found the mass adsorbed for 0.1 at temperature 1 and pressure 1, and for the mass absorbed at point 2, we take the information at the temperature 2 and pressure 2. Okay, for the pressure swing, the working principle is the temperature is increased from T1 to T2 and loading will be decreased from M1 to M2. So the delta loading is the same, M1 minus M2. Okay, the working principle for TSA, the cycle is between low and high temperature. This cycle help to load and regenerate the absorbent. Okay, the difference of PSA and also TSA system. PSA use shorter cycle time because there is no heating or cooling. Estimated around 5 to 60 minutes per cycle. For the TSA, it required longer cycle time for heating and cooling of bed and vessel, normally around 60 to 200 minutes. This because to allow the process of heating and also cooling. Okay, for the PSA, it requires multiple beds for high recovery and purity. It will use pressure balancing and purge to get better recovery and purity. So normally for the PSA, the common type in industry is 8, 10, 12 and 16 bed plants. So the application for the PSA is hydrogen purification and also air separation. Okay, for TSA, we need the additional equipment, for example heating and cooling equipment. So normally it will use a purge gas for region, for example like steam, nitrogen or slipstream of product. Okay, for the TSA it will need a fewer beds because we do not need to pressure equalize. We did not need to perform the pressure equalize. So the application for TSA is gas drying, VOC capture, CO2 removal in cryo plants. Okay, actually we have a few more application on TSA and PSA. If you want to know more about this, you can try to find the information inside the internet. There is so many research covered on this PSA and also TSA. Okay, so this is the example of the real plant of the 12 bed PSA units. It consists of the surge tank, valve skid, and also absorber vessel. Okay, now I move to the membrane separations. Okay, for the membrane separation, basically it is a thin membrane of polymer or metal can be used to separate gases. So in a membrane separation, different species diffuse through a thin membrane at different rates. And also different gases have different solubility in metal or polymer. Okay, there is two terms, the two important terms inside the membrane separation, which is permeate and also retentate. So permeate is actually a flow that passes through the membrane and it becomes enriched in faster or more soluble species. Retentate is a inverse from permeate, which is the flow that does not pass through the membrane and becomes enriched in slower or less soluble species. Okay, membranes have relatively low cost but cannot obtain high purity or recovery. So basically this membrane separation is widely used for a bulk separation of gases. So this is the asymmetric membrane. Okay, we have a dense layer and porous support. Okay, normally the polymer membrane are usually cast as a asymmetric membranes. So it have a thin, dense, active layer. So this layer is supported on a thicker, stronger porous layer, like they mentioned inside the figure. So the backing close is used in some cases as support for active layer. Okay, this is the type of hollow fiber membranes. We have feed here and we have retentate here for the flow that cannot pass through the membrane, and we have a permeate part here for the flow that can pass through the membrane. So this is basically the membrane. Okay, this is the membrane cross sections. Okay, the membrane is cast as long thin fibers. Okay, a bundle of fiber is set into a resin coating. Okay, it's set here. So it will form a tube sheet. The feed here is fed in this shell side. Basically, this equipment is same configuration like a heat exchanger. If you can remember back on a heat transfer. So the feed will permeate withdrawn from inside the fibers. Okay, so this is the membrane module. So we can see that the membrane inside here. Okay, there's another type of membrane, which is flat sheet membranes, which is in a shape of spiral. Okay, so in here we can see that membrane are cast as a sheets. These sheets are glued back to back along the edges to form an envelope. So we can see the shape of envelope here, and it attached to the perforated tube here. So the assembly is then rolled up into a spiral wound module. So you can see here, it's like a spiral wound. So the feed will go in here and it will start to flow inside the membranes. The one that can pass through will permeate here, the one that cannot pass through will retentate here. Okay, so this is the illustrations for the microscopic analysis of the membranes. We can use the SEM, SEM, TEM, and also STEM to see this figure. So inside the membrane, actually we can see there is a porous support layer here. So porous, there is a pore here, right? So and also there is a thin selective skins up here. Okay, so for the membrane flow pattern, we have three types, which is counter current, co-current, and also cross flow. Okay, same like a heat exchanger, right? So the mechanism is the same. The flow pattern, what I mean is the flow pattern is the same, but for the heat exchanger, there is a heat transfer occur, but for the membrane, there is a separation process occur. Okay, for the membrane process performance, okay, normally the membranes give low recovery of permeate species, which is around 95% maximum. Normally it's 90%. So for the membranes, we need to maintain a high enough partial pressure on retentate side to give reasonable flux at the outlet of the unit. So if the outlet partial pressure is low, the flux is low, and area required become large and costly. So unless the selectivity is very high. So when the selectivity is high, so the membrane can give low priority on permeate side around 98%, but normally it's 95% only. So these membranes usually are used for bulk separation like aspiration, CO2 rejection from natural gas, H2 recovery from mixture with methane. So basically for aspiration, we use hollow fiber, and CO2 rejection, we use the spiral wound. So this is the membrane module inside the industry. So this one is an example for the rejecting CO2 from natural gas. Okay, for the vapor liquid separations, there is a few type of equipment can be used. It's depending on your separation aims. If your process want to do the multiple stage separation between identified light key and also heavy key, you can use the distillation. If your process want to use the single stage thermal and phase equilibrium, you can use a flash tank. So if you want to do a stage removal of volatile solid or solvent, you can use the evaporation. If you want to remove the vapor component using non-volatile solvent, then you can use the absorption. If you want to do a separation of multiple components mixture into fraction by boiling ranges, for example like oil refining, you can use the fractionation. So normally the fractionation is used to separate the hydrocarbon. Okay, for the stripping, normally can be used for the multi-stage removal of volatile solute from solvent. Okay, for the liquid-liquid separations, we have 4, which is decanting, mixer settler, extractions, and also membrane. So decanting normally is a single stage thermal and phase equilibrium. For extraction, we have a multi-stage contacting of 2 liquid phases. Okay, you can choose the type of separator that you want to use based on your necessity on your process. Okay, for the mixer settler, normally it is a single theoretical stages extraction process. It also can be used for 2 or 3 stages and still cheaper than a column. For the membrane, you can use based on the differences in relative permeability of components. Okay, this membrane can be used to keep the two solvent from mixing. Okay, this is the example of multi-stage extraction for the sulfonyl process. Okay, basically this process is used for the liquid-liquid extraction of benzene and toluene from gasoline. Okay, basically the feed is fed into the extractor and then it will come out with the top product, which is raffinate, and the bottom product will go to the further process, which is stripper, to do the further separations. Okay, and then the top product will be recovered or recycled back to the extractor, and the bottom product will move to the next stage, which is recovery column. And after the recovery column, the product is extracted to the treating and fractionations, and the bottom product is recycled back to stripper, and some of it will recover back to the extractor. Okay, this is the example of circulating magma crystallizer. Basically, this process to separate the crystal like ruby, topaz, the mixture inside the magma. The magma, if we process, we can get a crystal like ruby, topaz, zircon. So basically, inside this process, the liquid will vaporize and move to the condenser. Okay, in here the feed will feed and go to heat exchanger, and then it will move to the crystallizer. At the crystallizer, the crystal will go down and become the and go to the product discharge. Meanwhile, the vapor or liquid will move upward and go to the condenser. So This super saturation can be achieved by evaporation or cooling. Okay, basically the crystallizer we have two types, which is evaporation and cooling. But in this magma crystallizer, we will use evaporation. So the liquid or vapor here will evaporate and go to the condenser. Okay, I think that's all for this video. So we will continue on the second part of 3.3. In the next lecture or video, I will inform back to you. Okay, thank you.